So in this video we're going to discuss obviously quantum mechanics, and I will describe basically what quantum mechanics is as a whole subject, and it's relatively new with the whole Einstein and Max Planck, everything that they discovered is all recent. It's modern physics. Einstein is the father of modern physics, and I'll discuss what he did and what everyone else did in the discovery for quantum mechanics. Now first, what does it mean to quantize something? Well, to quantize something is basically to subdivide it into smaller things. This is something important to understand, as if you say something's quantized, it's made smaller, subdivided. So, when we first approached quantum mechanics, we questioned a few things. One was the nature of light. What is light? And that's one of the questions that Einstein asked. He didn't know what light was, and he also pictured himself riding on this light beam, daydreaming, and seeing what would happen in that instance. What would happen also if he traveled at the speed of light? When the speed of light was also traveling at the same time, what would happen? Would the speed of light always remain ahead of him like previous people thought? Or would it actually appear to go static still, because relative to him it was traveling the same speed? So basically we analyzed the nature of light, and the electron is the most principal thing to this nature of light. Well, then we ask, well, why is the electron so important? Well, within different elements, they have different orbitals. And within these different orbitals, they have principal levels of energy. Higher level means higher energy, right? So, when the electron goes down into a lower energy level and drops, energy is actually emitted in the form of, well, light. So it's the electron dropping down. The principal energy level makes light. That's basically what the conclusion is. Except we need to analyze first how this all started. Well, it kind of started with Newton again, and everyone had a certain role in it, like Michael Faraday, you could say Lavoisier. All of them had a role in describing what quantum mechanics really is. But the main people associated with quantum mechanics are Max Planck, Einstein, de Broglie. Um, you also have there's other important people like Schrödinger, um, and that's Heisenberg as well, because the Heisenberg uncertainty principle. That those people are basically the principal forerunners of modern quantum mechanics. And in fact, a funny little fact is that the Prime Minister of Germany currently has a PhD in quantum mechanics, which I think that is very interesting, as it's probably very difficult to get a PhD in that area. It's one of the most more harder areas to understand, especially with quantum theory. Now this video is going to be a little bit basic on what is the overview and how to calculate certain things based on quantum mechanics. But first we start with Max Planck, who was actually Einstein's mentor. And this was around Germany during the time of just before World War I. This first happened that, well, Max Planck and Einstein teamed up much later, but Max Planck kind of had this idea first about quantum mechanics, this questioning of what is light. Then Einstein kind of took it to a different level and made his own theories. And that's why Einstein is so important. And Einstein basically discovered the photoelectric effect in 1905. The photoelectric effect in 1905, which he was actually, I think, given the Nobel Prize for, if I'm not mistaken, because his theory of relativity is a little bit debatable. So the photoelectric effect basically said that Light has it's packed into these packets. Packets of light are called photons. And so photons hit a metal or a non-metal, but for our case it would be a metal more likely. It hits a metal, it shines. The metal is going to emit an electron because of the photon energy that's hitting it. Okay. And there's certain energy that has to be satisfied in order for the electron to be emitted, because in certain cases the electron will not be emitted, but the photon will still disappear. You also have the creation of the two twins, positron, and there's a positron and I think a neutron or something that comes out also that can be created from the photon hitting something. Uh, Generally, you can't really see a photon hitting something, so it's a bit hard to picture this. But moving on from the photons and the photoelectric effect, we have de Broglie, which he described that the wave is kind of the wavelength and such come kind of like particles, and he associated waves and particles in the same sentence, that they're kind of the same. So then, well, we have Einstein. Now we all know Einstein proposed E equals mc squared, where energy equals the mass times the speed of light squared, in order to find the energy given off from such quantum calculations that he needed with the electrons. But we also had another formula that was more of Bohr and Rutherford. Like, Rutherford did more radiation work with gamma rays and whatnot with his gold foil experiment, but Bohr was more into the quantum mechanics, and that's where it kind of started initially too. And so, if you're going from a higher level, a principal energy level, to a lower, like if I had n equals 6 to start with, and then my final one is n equals 2, there's a way to calculate this. The way to calculate this is using this equation. RH all over H times 1 over Ni squared minus 1 over Nf squared. Okay, now RH is kind of Bohr's constant. There are many different constants that comes with this territory. The RH, well, this calculates the frequency, by the way, I should specify. And then you can plug that into another formula, which I'll show. The RH is Bohr's constant, which is 2.18 times 10 to the negative 18th. And then the H is Planck's constant, which is 6.63 times 10 to the negative 34 joules. And then this 1 over Ni squared. Ni is the initial principal level, and they square it, minus 1 over the final squared. Now we're going to get a negative result if our principal energy level is, let's say, 6 to 2, all because we're going from higher to lower, which is going to emit energy, which should mean that the thing should be negative. It's going to be negative. We calculate the frequency from this though, and then once we get the frequency, we plug it into V, which is frequency, lambda equals c, which is the speed of light. So in other words, if the frequency is one such number, plug that in here, I can divide out, I get, well, the V, the frequency, is equal to the c over the lambda. And lambda is the wavelength. And so, in other words, if I want the lambda's got to be the c over the wavelength, over the frequency, right? And the c is 3.00 generally times 10 to the 8th meters second, and that's what we generally use to calculate these things. In other words, you just plug that into the equation once you get either frequency or wavelength. Plug that in, and then you'll get the other, frequency or wavelength. Okay. We also have another equation which is E equals HF, where F is the frequency and E is the energy calculated, and H is Planck's constant. That's how you find the energy just from the frequency itself. So that comes in handy quite often, actually, more than other equations. Then we have A equal H over mv squared, which is this is actually going to be wavelength that equals this. And this is used to calculate more so if you get mass and velocity. And H is Planck's constant. And so with that, that's how you calculate those things. The Heisenberg uncertainty principle, something we should discuss right now, is when you can't calculate if you're trying to calculate the velocity and kind of the position of the electron at the same time, it can't happen. This is what Heisenberg concluded. But also, I just want to write E equals mc squared over here. The E equals mc squared is actually more of a derivation from all these equations that we have up here. He took all of them and just shoved them all together basically, and said, okay, that means that the matter and the energy calculated from this are the same. And since then, it's been associated that matter and energy and light are all associated together. But then also, I want to talk about the orbitals of the electrons. We have the S, P, D, F, where S typically holds up to 2, P typically holds up to 6, D holds up to 10, and F holds up to 14. The periodic table is wonderful in that it's associated with how to find the orbital of any element, really, just using the table. If you know how, there are certain sublevels and blocks that you have to take. It's much like, if I had a table in front of me, I would show, but it's much like the 1s. If we have our first column over here, and then we have a second column. This first column going down are the alkaline metals. Alkaline earth metals are the second one, right? So going down from over here, this is going to be the S blocks over here. But depending on which S block you're in, you get 1s2, 2s2, 1s1. This is like the 1s1 block. This is the 1s2 block. Depending on which row over here that you're in, if it's like 1, 2, then it's 1s2, 2s2, or 1s1, or 2s1. And then over here we have the transition, which we have the 3D block, and it goes 1, 2, 3, 4, up to 10 is how you can tell which D that you're in. And then over there we have the P, we're near the noble gases, where P6 is typically the noble gas area. So then you can just go from the noble gas over there, and it decreases from 6 on until you hit boron kind of column, which is the P1s, still dependent on the row calculations. To get to the F, we have a little bottom area with transitions, the lanthanide series, where it kind of cuts off and goes to a different series. And we read it left from right, by the way, and that's how you get it. But the lanthanide series have F blocks, the 4 and 5F, which are down here. This is like the 4, and the bottom one is below this is going to be the 5, and these can hold up to 14, and depending on which one, it goes 1, 2, 3, 4, up to 14, and that's how you calculate that. And then you go to the D, and you go to the P, because this is the S, this is the F, if you're going in there, to the D, to the P, and that's how you calculate the econfig. I'll show you that in the next video, the examples. So that's all. If you have any comments, feel free.